Hi and hello once again to all of you. So we will discuss further on lesson number 6, transmission and distribution. The first topic, which is parameters of the line, and our second parameter that we will discuss today is inductance. So from our last meeting or last slide, we discussed R, or resistance. R and L are connected in series in a transmission line. So we describe a little bit of this one when we have our AC circuits, wherein we can get XL obviously by multiplying it by the angular frequency, which is the omega, which is 2 pi f. Okay, now the inductance is this is based from your physics, is simply equal to the flux linkage. So the flux linkage is your Weber turns. So it has here an equation of the number of turns times the flux. The unit of the flux is Weber, and N is dependent on the number of turns. For example, you have a coil, so the phi here, or psi to be exact, is flux linkage is N times phi. And it is also inversely proportional to the current. So it is also the same thing with the skin effect, because on the skin effect, since you're running in AC, the inductance will have a major effect on the computation of the resistance, simply because the larger the inductance, the lower the current. Okay, now, in an inductance, this is also the same principle in a single phase 2-wire line. You're computing the loop inductance. So getting L here is always twice of the L, or L per conductor. This is also the same principle on our resistance. And if you have a 3-phase line, inductance must be balanced. If there's a mutual inductance involved, your Y matrix or even your modeling on your transmission line will have a different configuration. But anyway, we will discuss a little bit of the transposition effects when we have another set of videos for the mutual inductance in transposition of lines. So for this, we will assume that the system or the transmission line is balanced as usual, considering L is equal to LA times LB times LC, or simply the inductance per phase is the same. Okay, now we have two types of configurations, by the way, on the transmission line. It can be a single phase 2-wire or a 3-phase 3-wire. So for a single phase 2-wire line, okay, for example, you have conductor 1 and conductor 2 respectively, and they are separated by a distance d and a diameter on the conductor, I could say d. By the way, we will consider first solid, because you have two types of conductors. You can be a solid, or it can be a stranded, right? So we will consider solid first. Now, the formula here is already a predefined formula. Okay, so this obviously, since this is a refresher course, it can be derived on your undergrad, but if you have a separate video for the derivations, we can do so. That L is equal to 2 times 10 negative 7 ln of your distance d divided by this r prime. The r prime here, by the way, is the equivalent radius of the conductor. And we have here in terms of inductor, because the equivalent radius is different when you go to the capacitance topic. So here, r prime is designated as your ds, or sometimes called self-distance, or sometimes called on its typical definition, which is the famous GMR, or geometric mean radius. So your RL here, or equivalent radius, or geometric mean radius, or self-distance of a solid conductor is 0.7788 multiplied by the radius R. Okay, so the 0.7788 here is, you consider your conductor as a hollow type material, and from there, since that is aluminum or copper, we can have an equation and derivation so that the self-distance, or the GMR, becomes 0.7788, or simply this 0.7788 is simply equal to E u raised to negative 1/4. This is the same thing with 0.7788. Okay, now, this, the distance between conductors. So we already described that one. And please take note, when you go to the total inductance, you must consider as well the unit. Okay, let us move forward to a three-phase, three-wire system. You have a three-phase, three-wire. You have three wires here, considering a three-phase source. And then you have distance D here. Okay, by the way, the from 1 to 3, you have twice D, obviously. Okay, now we will consider another definition here. I could say DEQ, since you're considering equivalent distance or mean distance of the three conductors. It is called as well as geometric mean distance of GMD, and it is also called a mutual distance, or simply, in other words, DM. The equivalent distance is simply equal to the cube root of the distance 1, 2, distance 2, 3, and distance 3, 1. So, you have this equation here, a very, very important equation when you go to three-phase systems in transmission lines. And you can now get your inductance here. It's the same pattern, considering aluminum and copper and hollow shell. Please take note, the 2 times 10 negative 7 equation here with the 0.7788 of R is only for aluminum and copper conductor only. If the conductor becomes different, well, this equation will become different as well. Okay, since typically in our transmission lines, we considered aluminum conductor and copper conductor as our main line, respectively. So we will consider this equation as well for shortcuts and more precise, because this is our approximates. Okay, you're not considering the internal inductance anymore. But anyway, I already checked that on some of my derivation on my classes. But anyway, if you've seen a 2 times 10 negative 7 there, you're considering aluminum and copper conductor, especially when you're considering this equation for the 0.7788. So the equation for a three-phase, three-wire is L is equal to 2 times 10 negative 7 ln DEQ all over DS, and it is in Henry per meter per phase or per conductor basis. So we will go to the next slide for the other derivations for the inductance, especially when you're considering bundled configuration. Hi, so let us continue our discussion on the parameters of the line now. So considering again, if your transmission line has a bundled config. Okay, from A and B, you have from the last slide, you have single phase, 2 wire. Then on letter B, you have a three-phase, 3 wire, considering solid. Now, how about if your conductor is in a bundle configuration? So, how can you interpret that in a figure? Okay, for example. Now, consider this. Okay, on C.1 here. Okay, so it means if you have a transmission line pole. Okay, for example, I will draw here a transmission line pole. You have your arms. Okay, this just for example purpose. Sorry for my drawing. Okay, and then your transmission lines has conductors, right? So it is not stated there the insulators. Considering you see the conductors here, I could say this A, B, and C. And we interpret that in every conductor you have 2 strands. One conductor, 2 strands. One other conductor, 2 strands. So you're considering this just a joke, like you have the nose of a pig. You have 3 pigs that has a nose, right? The nose of a pig, right? So here you have his conductor A, conductor B, and conductor C, and these are your nose of the pig. They have 2 conductors. 2 strands in a conductor. So in a conductor you have 2 strands, and they have separated by a distance D, smaller d, and it is also separated by a distance D per conductor. So please take note, the D here, the bigger D is per conductor distance, while the D that is smaller is for strand distance. So without further ado, so that is one example to illustrate a bundled configuration in a transmission line. So for that, you have L is equal to 2 times 10 negative 7 ln DEQ all over DSB. DSB is considered as your bundled configuration for your self-distance or GMR of a bundle. Okay, which is the unit is Henry per meter per conductor. Okay, let us have the formula, the secret form. But anyway, this is not already a secret because I already illustrated here for you. Okay, that if you want to get the formulas here, okay, by deriving it on your own, and it is also important on some of the different types of configuration, that the geometric mean distance, or geometric mean radius of a bundle is simply equal to the n squared, then the nth root of the product of n terms. So what is the n here? Is obviously the number of strands. Okay, so what is the, how can you apply this one? So we will have an example, and then if you already know the principle itself, you can do that on the other type of conductors. Okay, so please take note of this very important equation, and as I have mentioned to you, all of the squared or the rectangular boxes here are the important formulas. Okay, for example, for a two bundle configuration, you have two strands, and please take note, okay, they are identical. All of the conductors A, B, C are identical, so we can only get one and then analyze the GMR of that. So example, using a GMR of your two bundle, and we will use the GMR formula here, product of n terms. So here we have one distance here, so D11, so that is the self, and then your mutual distance to 1 prime. So this is D11 and D1 and 1 prime here. Okay, and then the other way around, the second conductor itself, okay, D1 prime 1 prime and then D1 prime 1. So these are the distances. Okay, by the way, I need to change this one so that you will not be confused. So instead of a capital letter, it must be a smaller letter, considering that is a strand distance. So please take note that the same subscript here, or the diagonal, the diagonal here, diagonal is simply equal to your self distance, or simply your ds of your solid strand. Please take note that is one strand. So that's a 1 prime, then 1 prime 1 prime, and then 1. So you need to arrange that in a matrix like this. So the diagonal here is simply your same subscript, 1 1 and 1 prime 1 prime, and your D1 prime 1 and 1 prime is simply equal to your distance D. Okay, so I already changed this one, so you will not be confused. Sorry for this, but anyway, since this is live, no problem. Okay, now, so the n squared there is simply equal to, you have two strands, then you squared, you have 4. So how can you counter check if your distances are correct? Your nth root must be equal to this exponent. So how many distances are here? You have 4. It must be equal to that nth root. Okay, since you have 4 and 4, yes, we already have a correct analysis of our bundle configuration and using that GMR formula. Okay, now by having that, okay, and then substitute and then simplify, we have the GMR2 bundle as ds times d. So please take note the ds here is simply your 0.7788 or RE negative 1/4. Okay, now since we have that simple example, you can already derive the others. So I gave here, okay, the formulas. But anyway, since if we have the time again to discuss comprehensively this topic, we can have this as in a separate video, but since this is just for refresher type, so I leave it to you, the derivation of the other configuration for the bundle type. So the typical bundle configuration for a symmetrical bundle is a triangle symmetrically spaced. When you say symmetrical space, equal spacing. So if you do the same pattern on the two bundled and using this formula here, and then we can arrive at this formula of the GMR 3 bundled symmetrical, which is cube root of ds times d squared. Please take note that d squared there is a strand distance. And if you do it on your 4 bundle configuration, the typical arrangement, so if there's no saying on the problem that what type of bundles, 4 bundle, because your 4 bundle can be a diagonal, your 3 bundle can be a vertical like this, a horizontal like this, or a vertical like this. So these are different configurations, right? So if you have a bundled diamond like this with the same distance d, of course, so that will be different. But if you say typical, if there's no given, you can use a square and a symmetrical triangle or equilateral triangle. So the formula for a 4 bundled is 1.09 square. 1.09 multiplied by the 4th root of ds times d cube. Okay, now this is the basic principles for your inductance. We will now go forward to the next slide for capacitance. Please stay tuned, guys.